Hello, I'm Matthew Goldstein, Chancellor of the City University of New York. Welcome to this special edition of CUNY Honors. As you may know, the City University of New York has declared 2005 through 2015 to be the Decade of Science at CUNY. This is a major initiative building on our long and distinguished history of teaching and research in the sciences and related disciplines. We are modernizing our science facilities. We are working to stimulate student interest and retention in the sciences, and we are educating teachers committed to teaching math and science in our city's middle and high schools. We must continue to expand our efforts to interest young people in the sciences, including students from traditionally underrepresented groups, so that our city, state, and nation may compete more effectively in global competition and in the marketplace of ideas. I welcome the dedication of our distinguished faculty as they guide all our students in their educations and careers. Indeed, at the core of our work are the members of the CUNY faculty, each one devoted to teaching and learning. With me today are four prominent CUNY scientists. Dr. Daniel Akins, professor of chemistry at the City College, has been a CUNY faculty member since 1981. He has directed the CUNY Center for Analysis of Structures and Interfaces. Professor Akins' principal research involves quantum properties of molecular nanostructures and the exploitation of such properties for formulating new nanomaterials. Among Professor Akins' many honors and awards is the Presidential Award for Excellence in Science, Mathematics, and Engineering, mentoring which he received in 2000. Welcome, Professor Akins. Dr. Mary T. Filbin is a distinguished professor of biology at Hunter College. She joined the biology department in 1990. Dr. Filbin has discovered a way to block the inhibiting function of the molecule MAG and all other inhibitors present in the myelin sheath that prevent the spinal cord from regenerating after an injury, a research breakthrough of great potential to victims of spinal cord injuries. For her work, Professor Filbin was selected as a co-recipient of the 2001 Ameritech Prize toward finding a cure for paralysis. She is the first woman to be awarded this prize. Welcome, Dr. Filbin. Dr. Myriam Sarachik is a distinguished professor of physics at the City College, which she began teaching in 1967. Dr. Sarachik served as the executive officer of the university-wide CUNY PhD program in physics from 1975 to 1978. She is an experimental condensed matter physicist and has published nearly 150 articles in professional journals. She is a member of many prestigious professional organizations, including the National Academy of Sciences and a past president of the American Physical Society. Dr. Sarachik was also named 2005 Laurel UNESCO for Women in Science Laureate for North America. Welcome, Dr. Sarachik.
Thank you.
And Dr. Charles Liu is an assistant professor of astrophysics in the Department of Engineering, Science, and Physics at the College of Staten Island. He works on observational studies of galaxy evolution and the star formation history of the universe. This includes the study of starburst galaxies, post-starburst objects, and colliding, merging, and interacting galaxies. Dr. Liu says that he has also dabbled in quasars. Dr. Liu is currently participating in two large projects, an international collaboration with MUSYC and a Hubble Space telescope treasury program called Cosmos. Thank you, Dr. Liu, and thank you to all of us.
Thank you.
Thanks.
And let me tell our audience that we have a number of live, bright, interesting students who later on in the show will have an opportunity to chat with our very distinguished panelists here. But first, to our panelists. I'm interested in what inspired each of you to follow your brilliant careers as they are in science. Was it a teacher? Was it your own motivation? What touched you at an early stage to get you to pursue the wonderful work that you do? Dr. Akins, why don't we start with you?
Well, thank you. I've thought about that. It's a very difficult and complex thing, in fact, for me to really know what interests me and got me started in science. But I guess if I had to say it was anything, it was the fact that there was such prestige and I guess excitement associated with people who could look at the unknown and provide answers. I think knowing that there were things that people didn't know and wanting to contribute to answers was the thing that excited me. And then, of course, there were some people who were just out-and-out heroes. Einstein, for example. I wanted to be a physicist. I ended up being a physical chemist, which is pretty close, right? And and as a result, I also was interested in mathematics, and so I married everything together: physics, mathematics, chemistry, and that's what physical chemistry does. Is all about.
Dr. Filbin, how did it start with you?
I was interested in science from I was 5 or 6, but I think I became a neuroscientist or involved in neurobiology because I remember a high school teacher drawing a diagram of a synapse on the blackboard and explaining that this was how two nerve cells worked with each other, communicated. And I remember thinking at the time, my goodness, this is how we think. These molecules, these electrical currents are the reason our brains work. So I think from that age, I must have been about 12 or 13, I became really involved in neuroscience, and the teacher inspired me, and I then went on to go into science. Now, I didn't plan to be a scientist. It just sort of happened that as I went along with my career, I couldn't find anything else that I really wanted to do, and science and neuroscience always came up on top.
So really at a relatively young age, with a teacher really inspired you, and you went on from there.
Yes.
Dr. Sarachik, you're a very distinguished physicist. Your bio indicates 150 research papers, more awards than I can list today, a past president of the American Physical Society. You've really done it all. Where did it start with Myriam Sarachik?
Where did it start? I was actually interested in many things. I was interested in literature, music, math, and I couldn't actually make up my mind for a while. I loved numbers. I always loved the way they fit together and just the way they worked. And my father, who did not have a chance to get a formal education, although he was one of the best self-educated people I know, always deeply admired and respected physics in particular, although he didn't expect me to study that or anything really because I was a girl, right? But then when I got into college and I did have to make a decision, I had to choose, and the mathematical and physical sciences always appealed to me. And physics, of all of them, was the biggest challenge. I didn't really understand very much at all in the beginning. I still don't understand that much, right? But it was a puzzle, it was a challenge, and it was fascinating. It was fun. So I just continued and continued and continued, and somehow I got to where I am now.
That's great. Charles Liu, you're a cosmologist, a physicist that studies very, very large phenomenon like galaxies and quasars and so forth.
Yeah.
How did it start with you? What got you interested in this?
Well, like Myriam, I couldn't decide when I was a kid what to do. I had all kinds of interests. Never mind the humanities and the sciences, I wanted to be an actor. I wanted to be a clown. I wanted to be, yes, a clown. And I wanted to be all these sorts of different things. And what I was very fortunate about was that I was given the freedom to explore. By my parents, of course they wanted me to study medicine and become a doctor. But they were totally okay with me not doing that, because it was clear to them that what I needed to do was to find out what I liked to do. All of my teachers, I had a wonderful public education in New York State, and I was very fortunate even through college. My professor said, you study what you want, you figure out what you want to do. And so the path was very gradual, and it was not until high school that I realized I wanted to do some kind of science. And it was my second year in college that I looked around me and my friends and those people who were studying science, and the astronomy department seemed the most welcoming. The place that was most able to address all the different things I wanted to do. Because what poet has not looked up in the sky and wondered what's out there? And yet what scientist has not wondered, why does the sun shine? How did the universe begin? What will happen to the earth billions of years from now? So it was a natural, I guess, progression that came to this point. And to this day, I'm still having a great time.
That's great. You know, my own interest is in mathematics and in the computational sciences and probability. And when I reflect on my own interest, I have some heroes. And we could talk about the great heroes in mathematics, but right before the show we were talking about books that we read and some of the great heroes that really created an inflection point. The road changed because of their work. This is not about me, it's more about the four of you. But Mary, who were some of your heroes, and how did they really make an enormous difference in the work that you do today?
Well, in neurobiology, the name that comes to mind immediately is Ramon y Cajal, and he's considered the father of neurobiology. Back in the late 1800s, early 20th century, he would do all kinds of experiments with the use of the Golgi stain. He was able to look at the formation of nerves in the spinal cord, in the brain. Excuse me, and if you look at his book now, he would draw very meticulously. He and his wife would draw what they saw down the microscope. And now, with all the techniques we have for imaging, you could almost just go and fill in those drawings with a colour as if it was immunofluorescent. It's magnificent. He was the first one to suggest that the environment in a nervous system was inhibitory to regrowth, not that the neuron had not lost the ability to grow. The other person who I think is a hero is Rita Levi-Montalcini, and she received the Nobel Prize in 1986 for her discovery of nerve growth factor, which was the first molecule to be identified that allowed a nerve to survive. And she had a professorship at Turin University during the Second World War, and she lost her position because she was Jewish, and she continued her work in her bedroom while the bombs were going off around in Turin. And subsequently then she received the Nobel Prize. So it's seemingly in Italy, when she walks into a room, everyone just stands up and claps no matter where they are. But I'd say those are the two heroes. One was a woman who didn't give up in the face of adversity, and Ramon y Cajal, I mean, we still refer to his work all the time.
Daniel, Professor Akins, several years ago, and it's not too long ago, if you use the term nanostructures or nanotechnology, people would look at you and say, what is that? So yours is a relatively young discipline, so your heroes, I would imagine, that led you into studying. You started as a physical chemist and really evolved into this. Who were some of those early people that really inspired you to do the great work you're doing today?
I sort of got into nanotechnology at its inception. Before coming to City University, I had a short stint at the Polaroid Corporation in Massachusetts. And of course, what we did was nanotechnology. We just didn't call it that. I mean, photography, in fact, you make latent images, which are nano-sized and smaller sites that you then activate or developed to get an image, and there's all types of chemistry and things involved in making that happen. So when I came to the City University, I naturally continued that type of research. And nanotechnology sort of got started at least, it took 20 years after Richard Feynman, maybe even more than that, 25 years after Richard Feynman, who's given credit, who's a physicist, given credit for challenging scientists to start thinking about using matter in a range of sizes where materials take on the properties that they exhibit once they become macro size. And he is famous for having titled his presentation, "There's Plenty of Room at the Bottom." So, and he talked about how you can write the whole Encyclopedia Britannica on the head of a pen, and showed that if you, in fact, if you made the size within a certain nano size, one could do that. Well, after I came to the City University of New York, it was natural for me to continue that research. Now, in terms of a hero, there's a funny story. I used to read a lot of work in this area. It actually started with the photographic field by a guy named Walter Cooper. And there were not a lot of black heroes in science when I was growing up. And I used to read this fellow's work. And one day, Walter Cooper was invited to give a talk at City University. And I walked out of my office, and there was the black guy and a lot of other people. They said Walter Cooper was there. I walked out, I looked around. But I have learned by making mistakes that you mature when you start recognizing mistakes over and over again, right? So, but this time I caught it, and I knew that this was a situation where I could make a mistake. And I looked at him, I said, "You must be Walter Cooper." And he laughed. And I told him that the reason I did that was that I came out there expecting him not to be black, and here he was. I was totally in average shock, but pleasantly surprised. And I've actually found, science. My heroes have been just events, not so much people, but challenges such as the space program. They wanted scientists, and there were a lot of challenging questions. So that naturally got my attention, a lot of other people's attention. Nanotechnology, that's the thing now, that there's a lot of opportunities, but I can tell you what the future is. And I can be almost 100% sure, because energy is the future. And the fact that this Earth is limited in its capacity to support life means that anything that's green, and if you could create help in the energy problem, then you really have a future. And I think, in fact, nanotechnology can do that, because you can make fuel cells using nanomaterials. You can increase the efficiency. You can figure out ways to sequester greenhouse gases, either sequester them or even reuse them, making energy or storing the energy. So there's all kind of opportunities in science to make a positive impact on humankind's existence on this planet.
Richard Feynman died about 20 years ago. Mm-hmm. And I think if he were alive today, he'd be amazed in the 20 years what has happened in the field of quantum mechanics and the kinds of things that you were referring to earlier. Mm-hmm. For our audience, for those of you who want to learn a little more about Richard Feynman, he's one of the great characters in science, but also an extraordinary genius. Charles Liu, it's got to be a very exciting time to be in astronomy and cosmology. Talk a little about some of the people that really influence you to pursue this field.
Oh boy. Well, the history of astronomy is almost like the history of all of science. Astronomy is the oldest of the natural sciences. There are a couple of points in the history of it where it really starts to shift, where you're just not looking anymore, but actually starting to explain and understand and describe what's happening. I think Galileo Galilei was probably the most important person who shifted that paradigm of science in general and astronomy in specific from just looking and wondering and actually going in and interpreting. He was the first person to use a telescope to look upward in the sky and saw so many new things and created almost by himself the concept of science and physical sciences in general, the idea of experimentation, the need to do and see and observe rather than just think and then guess. So Galileo is real big. In fact, my older son's middle name is Galileo, and yeah, my wife was a little perturbed about that, but that's okay. She went with the middle name. I was going to say, well, let's make it the first name, but she said, no. I said, okay, middle name then. Okay, so that's sort of how important Galileo really is in the whole process. And then another major transition was right around the end of the 19th, beginning of the 20th century, where astronomy was going from a descriptive science, explaining, seeing what they were and trying to just things about watching them move and things, to really transitioning to putting a real physical framework into it. And that was really around the time that astronomy and astrophysics became synonymous. To this day, when I refer to myself as an astronomer, our professional organization is called the American Astronomical Society. It's one of the sister organizations of the American Physical Society. But we call ourselves astronomers, but the term astrophysics has become ubiquitous and synonymous because we really do study the universe primarily through physics, though also with some biology and chemistry. So that transitional time, there's so many heroes during that time. Annie Jump Ken and Henrietta Swan-Leavitt, Cecilia Payne-Gaposchkin, Edwin Hubble, and the greats of physics as well, Albert Einstein, Max Planck, and so many others. So it really is a shoulders of giants kind of thing. And of course the person who said that, Isaac Newton, is another one of the greats that made it possible.
Great segue into my question to Professor Sarachik. The first part of the 20th century, the first 2 or 3 decades, is viewed by many people to be the modern age of physics. You mentioned Max Planck, but Pauli and Schrödinger and certainly Albert Einstein.
And mathematicians, too.
Mathematicians. And we'll get to why mathematics is really the mother of all of these disciplines. But you came of age as a physicist in the 20th century.
I did.
After all of these great early men and women were doing...
Not too many.
Lisa Meitner,
yes,
was one, sort of Madame Curie, I mean, certainly another. Emmy Noether, although as a mathematician.
Profound, yes.
Who were those heroes for you? Somehow I have a feeling I know what the answer is, but I'd like you to say it yourself.
No, because I don't know what the answer is either.
Okay.
Because I was thinking as the rest of you were talking, and there is a very, very long and distinguished history, mathematics and physics, starting with Archimedes, for example, Leonardo da Vinci. Galileo is actually one of my real heroes because Galileo Galilei stands for me for speaking truth, regardless of circumstances and regardless of the dangers. You know, he had a history. And Newton and Gauss and Kepler, all from, you know, Kepler from your end of things. And then and Faraday and Tesla. I mean, the names are, they just
the list goes on.
The list goes on. And then at the turn of between the 19th and the 20th century, it was the dawning of what we call the modern era of physics. And it was truly spectacular for a 30 or a 40 or a 50-year period, and it actually continues. There are new discoveries being made that people don't really understand or know all that much about yet. And the names are clear. I mean, Newton, by the way, has to be in there. He was much earlier.
A giant.
Much earlier. But then Einstein was truly a giant. I mean, with Einstein, There was special relativity, which is absolutely beautiful. There's general relativity. There is quantum mechanics, which he had some serious doubts about in his later life. He said God does not play dice with the universe, right? Schrödinger and Dirac, and the names just abound. The history is not really what drew me to it. I think it's the fundamental aspects of it. It's trying to understand the world we live in, and putting it together at a fundamental level that drew me in. And of course the things you can do with it are things that flow out of all of that and is also very important. But what drew me was like the theory of numbers, right? It's the fundamental pieces and how they fit together and why they work the way they do.
Let's talk briefly about your work and where you see it going. Mary Filbin, your work around spinal cord regeneration could have a profound impact on the lives and better living for hundreds of thousands of people, if not more. Where do you see your work going, and are you optimistic about the fundamental work that you're doing, translating into clinical trials? And talk a little about that.
So I'm interested in why spinal cords, nerves, and the central nervous system, the brain and the spinal cord, don't spontaneously regenerate after injury. And we know now that there are inhibitors in the damaged or diseased CNS that actively prevent nerves from regrowing. So what we've done is identify what these molecules are, how they inhibit a nerve from regrowing, but more importantly, we're trying to identify parallel pathways that will crosstalk with this inhibitory pathway and block it and allow the nerve to grow. Now, when I first came into this field, it was very serendipitous. We were looking at a particular protein. We thought it was going to be beneficial for growth, but it turned out it inhibits growth. And that was back in 1994, and then there were no molecules known about why spinal cords didn't regrow. If we look at now what we know, the information we have now, there are numerous places where we can intervene in these pathways and encourage regeneration. So there are some treatments that are already going into clinical trial at the moment. Some are in phase 2 clinical trial. And I would be cautiously optimistic. Maybe we're not going to make people walk immediately, but we're going to have some improvement in their function.
I'm going to take some authority here because this is such an interesting conversation. I just want to push it a little further. In a minute or so, tell us about some of the monumental things that astronomers are going to be able to investigate that they perhaps can't right now.
A minute or so. Well, let's see. In about 10 to 20 years, we're going to start making headway to understanding the creation of the first stars. How did the first stars form the first galaxies, the first black holes, the James Webb Space Telescope and so forth, new technologies. We'll also start to get some sense of gravitational waves. How does our universe interact with space and time itself? And perhaps even other spaces and other times, other universal structures. For example, the string theories are going to start to be able to be studied, not from gigantic scales, but on tiny scales as our particle accelerators get more and more powerful. And we've just started to realize that our universe is filled not primarily with the stuff of ourselves, protons, neutrons, electrons, but with dark matter and dark energy. We give these weird and vague names to dark matter and dark energy because we have no idea what they are. And yet for every ounce of protons or neutrons or electrons that exist in the world, there's a pound of matter that is nothing like that. And then there are many pounds equivalent worth of energy, which we have no idea what's happening. So I'm going to be in business for a long time. Astronomy doesn't change the price of bread today, but it could change the course of civilization tomorrow. And what we're doing is trying to figure out what that 95% of no idea is.
That's a great way to segue. We're going to take a very brief break, And when we return, we're going to have an opportunity to exchange ideas and answer some questions from these very distinguished students. So stay with us. We'll be right back.
Hi, I'm David Bauer, winner of the 2005 Intel Science Talent Search and a CUNY Honors College student at the City College of New York. I decided to come to the City University of New York because it is undergoing a tremendous scientific renaissance. CUNY has more than 100 nationally recognized science centers and has received hundreds of millions of dollars in research funding. CUNY is one of the nation's major research institutions. Chancellor Goldstein in 2005 declared a decade devoted to science at CUNY. If you are an aspiring scientist, join us. Call 1-800-CUNY-YES or visit our website at cuny.edu. That's 1-800-CUNY-YES or visit cuny.edu. Remember, invest in CUNY, and CUNY will invest in you.
Welcome back to this special segment of CUNY Honors. I'm here with four of our very distinguished scientists at CUNY. Daniel Akins, on my left, a professor at the City College in chemistry. Mary Filbin, a professor of chemistry, biology, but you work in chemistry too. At Hunter College, to my right, Professor Myriam Sarachik, who's a professor of physics at the City College, and Professor Charles Liu, a professor of physics, astronomy, and a whole bunch of other stuff at the College of Staten Island. Now is the time that we ask our students if they have a question that they would like to pose to one of our panelists here. Just raise your hand and the microphone will come. I ask you to state your name, where you are a student, what you intend to study or are studying, and then direct your question to one of our panelists.
My name is Harris. I attend City College. My major is biochemistry. And my question is aimed to Dr. Akin. You said you're working on nanotechnology. And one of the fascinating things about nanotechnology is the quantum dot. I was wondering if you're working with the quantum dot currently, and what are the future prospects for this?
Well, I should point out that, yes, I do work with the quantum dot. But I also work with in a center where quantum dots are used over a whole range of applications. I personally have used them to basically be structures on which other molecules can absorb and then create new energy states, and to exploit those new energy states that don't occur except in that environment for device applications, such as making new types of lasers or bright sources that one can characterize the medium in which the material might be. And of course there would be applications in biology for that type of thing. The center that I'm involved with, we just had a Nano Day in New York event, which I helped chair with Columbia University. We had a Nobel Prize winner, Horst Stormer, who talked about nanotechnology, nanoparticles, and made the analogy with sizes. In fact, he made the analogy with the cosmos. If you go out to great dimensions, in fact, it's mind-boggling. I mean, as small as nano is, if you start thinking about the galaxies, and I mean, it makes nano seem big. You know, so we work with nanoparticles, but there's so many other things that we're doing with nanotechnology. Nanoparticles is just one small aspect of the whole field of nanotechnology.
I just want to comment that the quantum dot is a type of semiconductor. It's used for tagging cells, and it's also used in transistors and stuff. I have another question, but it's aimed at the professor on the furthest left. You spoke about how astrology is going to be changing, and such a
astronomy.
Astronomy. In ways that we can't imagine. And I'm wondering if this is just a saying, because I heard so many pseudosciences come by and forth, and I just want to know what exactly will change. Like, it seems so big, and like, what small changes will you be, what small things will you be doing and studying from that?
Well, everything is always changing, right? And we can look at grandiose questions and we can see them one little bit at a time. Your point of what you're saying, astrology, is a slip of the tongue, but it's a very valid point. And then you mentioned pseudoscience, right? The question, what is the difference between science and non-science? And the answer is that the non-science stuff doesn't go through that rigorous process of looking at facts and trying to create hypotheses that eventually spawn predictions that are either proven or disproven. Either they stop at the hypothesis point, you know, you can say, aliens did it, and that's it, the end. You can't prove anymore, so that's not science. It just sort of stops there. And so when we're talking about scientific advancement, we are talking step by step by step. You said you heard so many things about all these strange things that are going to change. Well, things do change, and they change very fast. In astronomy, for example, and I think this is probably true for all the other sciences, the total amount of information, scientifically valid data and publications and so forth, doubles every 15 years. So even small changes make a gigantic difference in the long run because you're doing it with so many other people. One of the things, specifically one of the small changes that I'm working on, for example, which might help you understand the question involved, is I'm studying galaxies and the star formation history of the universe. Now, stars are very small, and there are 100 billion plus stars in our galaxy alone, and there are 100 billion or so galaxies just in the part of the universe that we can see. By just studying one star at a time, or one galaxy at a time, we get an example of how a system works. A recent set of stars that I was studying, 100 billion galaxies, 100 billion stars over here, 100 billion stars over here, crashing into each other at 1,000,000 miles per hour, but they're so large that it took over 400 million years for them to pass through one another. And in the meantime, all that interaction happening, stars forming like firecrackers, a black hole forming in the center. When are all these things all happening? Every person in my field has to basically take this gigantic question and narrow it down piece by piece. And so I was looking specifically at how old the stars are. Did the stars start forming all at once at the beginning of the collision or at the end of it? The supermassive black hole at the center, when did it form? Did it form at the beginning collision, or is it just now forming? Is it very bright now? Was it bright in the past? Those kinds of things. Bit by bit, we're putting together all the information. 50 years ago, the concept of a black hole might have been considered pseudoscience. The word had barely been coined by Professor Kip Thorne at Caltech. Today, we know that there are millions of black holes in our galaxy alone, and billions of black holes, some of them millions or billions of times the mass of our sun, in our observable universe. So that's how the process is going to go forward. I can't tell you what amazing discovery is going to happen tomorrow or next week or next year, but piece by piece, these big questions will be chopped up into little questions. Hypotheses will spawn predictions, which will either be proven or disproven, and then we'll continue to move on. That's the process of science.
Next question. Yes. Identify yourself, please.
Hi, I'm SOUMITRI SESHADRI from the College of Staten Island. Again, my question is directed towards Dr. Liu. I know you said earlier that you're all doing research about how the universe started, the Big Bang theories and all that. Have you ever given a thought about how it's all going to end?
Absolutely.
Because I heard a couple of people say that, you know, it's going to end because the universe is expanding and Earth will eventually fly away from the sun and you'll have no more source of energy. And also the sun itself is getting bigger and, you know, eventually will blow up and melt away all the planets, including us, everything. So what's your thought about it?
Well, what you've described, about 60% of it is right. And there's 40% of it, there's more. But that's good. You're in a good ratio, actually. That's very good. The thing is this. The concept of when the universe is going to end or how it's going to end is actually what led to our realization that there is this dark matter and dark energy that we described to begin with. The issue of the ending of the universe fundamentally comes down to gravity. If there is enough matter in the universe, if the density of the universe is high enough, then eventually the gravity will actually pull on space itself and stop the expansion and then bring it back down and crunch it into a reverse crunch. Time will start to run backwards as we know it, and our universe will collapse back into one tiny point. If there's not enough density, then the universe will expand forever and ever and ever. And the Earth will not fly away from the sun, because the Earth and the sun are gravitationally bound. But the expansion of the universe will carry the galaxies apart. And eventually the only things we see in the sky are the stars that are bound by our galaxy's gravity. And what will happen is that, yes, 5 billion years from now, the sun will expand to approximately 100 times its current diameter, and Earth will be crisped. But then the universe will continue to go on. I think about a Google years, 10 to the 100 years from now, matter, black holes, subatomic particles all decay, and we just wind up with nothingness. The universe will end not with a bang, but a whimper. That's what we know for now.
So they can just worry about their courses.
Oh, yeah, yeah. Don't change your graduation plans. You got a long time to go.
Okay, question over here.
Hi, my name is Roger Lee, and I'm currently a student at City College, and I'm majoring in electrical engineering. And my question is very general, and some of you hinted towards the answer before, but I was wondering if you couldn't be in your major now, or you had to change, like choose a different career path, what would you guys choose, or girls choose? And where would you go?
In today's world, guys is gender neutral. So
yes, of course.
Women and men respond to guys. Go ahead, why don't you start?
You know, I've asked myself that, and I have friends who've asked themselves that, and I know what they feel, but I personally couldn't see myself doing anything else. I had a chance to be in industry for a short period of time, very short period of time. I ran a program at the National Science Foundation as a rotator, where they take you from a university, put you in a management position, and I did that, you know, managing money and doing site visits to places, did that, and doing in academia. So I sort of seen all three worlds, if you like, and I really don't think I'd want to do anything else. It's mainly because you're not just doing one thing. You can start off being very much absorbed in your specific small effort. You can grow and change direction. It's really up to you. There are not very many fields that you can grow with it and define which direction to go. One thing I want to tell you in terms of the question over here, as a more pragmatist, I think my big concern is the next 200 years, because you know, this world can disappear in that period of time. Global warming, as an example, can possibly lead to the cessation of life on this planet in a very, very short period of time. And so there's a need for people to be involved, to find solutions, to deal with the energy crisis. We don't have to be passive witnesses to the demise of our galaxy, if you like.
Do you want to respond? Sure.
I've had a great time. And I was thinking about your question, which I think is a very interesting one. The choice I was really trying to make was whether to become a musician, a pianist, or to go into the sciences, physics in particular. And it seemed to me that I would probably not make it to the top ranks in music, which is what I would have wanted to do if I chose to do music. But that to be not a top rank physicist was less unacceptable to me. In other words, doing physics at a somewhat reduced level would be perfectly satisfactory, but doing music at a below top level was not acceptable. So I decided to go into physics, even though I was very much tempted to go into music and become a world rank concert pianist. That was my dream. I have to tell you, I don't know what I would do if I had it to do over again. But I actually became a top-ranked physicist, to my own surprise, and I have had a marvelous time doing it. I've had enormous fun. It's been an extremely interesting and challenging life. I've been doing what I want to do and being paid for it to boot. I started out at Bell Labs as a postdoc doing only research, and that's what I thought I wanted to do, nothing but research. But coming to a university has really given me opportunities to do so many different other things, to teach and to take a hand in university and departmental affairs, to travel, to present papers, and to do research, which is my first love. So I don't know the answer. Maybe I would try this time to become a musician.
You know,
Maybe.
Professor Sarachik, as I listen to you, and I listen closely to the rest of you, you all have a bunch of communalities. But one is that you love what you're doing. And I think if you don't love what you're doing, it's very hard to do good work. And I would surmise the four of you have to do the work that you're doing because you're so drawn by something that has such passion and import to your life. And I think that is really a great blessing.
It is.
There aren't too many people that get up in the morning and say, I want to do what I'm doing and I must do what I'm doing. And I think that really is so fundamentally important for people like yourself who do extraordinary work every day. Question over here. Yes. Let's wait for the mic.
Hi, my name is ROXANNE and I attend the City College of New York. And my major is biochemistry, so I have a biology question. You mentioned that the protein inhibits basically neurons from growing. Is there any chance that perhaps without this proton that there would be uncontrollable cell growth, namely cancer?
Well, the protein we work on doesn't affect cell proliferation, which is what happens in cancer. It only affects the nervous system, and it only affects nerves that are trying to regrow. So the argument, what I thought you were going to ask was, why has this protein evolved? Why do we need it? Why should we stop nerves from growing? And we don't know the answer to that. We can speculate and say, well, you know, if you damage a spinal cord, it's better to have no growth than to have aberrant growth. You get too much growth and you innervate the wrong targets. Now that's a speculation. Personally, I don't think it's true. I think what it is, this protein actually may stabilize the axon in the intact nervous system, and its ability to inhibit growth is just an aberrant carryover. It's not really meant to be doing that, but it does in the damaged spinal cord.
Thank you.
Sure.
Yes.
Hi, my name is Dan GURDAK. I'm a senior at Lehman College, and this is another question directed at each of you. We were discussing scientific heroes earlier, and one of my scientific heroes, E.O. Wilson, once said that young scientists should find a field, an unknown field, and make it their own. I know that I could probably spend an afternoon with each of you discussing this alone, but I was wondering if each of you could maybe comment very briefly about some advice for aspiring scientists and biologists and chemists and physicists that you may have. Just any advice.
Great question. Great question. Charles, you look like you want to start to answer that.
Come to the College of Staten Island. Come to CUNY. Really, in all seriousness, we really are building some wonderful things here. Chancellor Goldstein and all the faculty, all my colleagues, I'm relatively new here these past few years compared to all of you veterans. But really, I have been so impressed as what's been happening. Here, we have expansion happening. E.O. Wilson is exactly right. Find places that haven't been explored yet. And I would say that when you are looking, let yourself go, just as I was fortunate enough to be allowed to let go and find whatever you'd like to do. It will come to you if you think about it. Sometimes it comes to you in the shower. Sometimes it comes to you while you're laying in bed wondering, you know, is there a God or whatever. Who knows? But keeping the imagination alive is what's most important. Science is blessed. We scientists are blessed because we actually we get paid for asking questions that we don't know the answer to. And so when you head in that direction, you're going to be in good shape.
Great answer.
Could I just
Mary,
add something?
please,
Yes,
sure.
because I do think about this, especially in molecular biology or neurobiology. It's so competitive. And a competitor of mine and friend, Dr. Muming Pu, excuse me, his advice to his students and postdocs is go to the textbook. You don't necessarily have to believe that everything that's in a textbook is true. And you take something that is believed to be true, and now the experiment was done 20 years ago. Now we have new technology. You can address it in a different way. And either you get a publication either way, either you confirm it with the new technology, or you disprove it, and you're off in a completely different direction. But so don't believe what's in the books just because they're in books. And the other important thing, I think, is being able to choose where to go, because there's so many roads that you could take when you have an idea or you get a result. And it's maybe getting advice. What does this mean? Is it worth pursuing? And I think those are two pieces of information that I would have liked to have had when I was a student.
Daniel?
I would suggest, based on just, I guess, what I've seen, you know, who gets the Nobel Prize, for example, that you should try to find a need. You know, something that is maybe not pressing now, but you know that somewhere down the road, that, and it's not necessarily that hard to identify those things. I really didn't think about science in that way. I chose science because I just loved the science. But there are some people who choose science or problems in science because they want to be famous. And I laugh as I say that because I hadn't thought about this, but my daughter's a dancer on Broadway. And when she was a little girl, you're talking about passion, scientists having passion. People on Broadway, they would not eat. They will give up life to do what they do. I mean, that's a whole different kind of ballgame. The passion that they have is phenomenal. But I asked her, what did she want to do? Because I wanted her to be a scientist, and she said, I want to be famous. so I think that that's a very important question, but I would say to you, just from my seeing how people have made a name for themselves, choose a problem that if you can solve it, you will be important, famous, and go after it that way. More, if you aim at the stars, even if you don't make it, you'll get somewhere that's very important.
Do you want to add anything, Myriam?
Sure. I think we've given advice at many different levels. So I don't know what level to choose. I think that I believe you live only once. I'm not coming back, right? So to find something that you really care about passionately, and if you look around and you look at the history of various fields, the people who have contributed are people who really did very passionately want to do what they did. You work hard, and with a good nose, you find the good things. So, you know, my advice generally is just find something you really want to make a commitment to. Work hard, because actually working hard can be painful. To learn to understand something that you didn't understand before, even stuff that's understood by others but not yourself yet, is a challenge. There is pain in it, but when you get past it and you do understand, it's just a marvelous, triumphant feeling. And if you really are working at things, the opportunities come up for something that really is different and special. And your nose has to tell you that that's what you should pursue. That's my advice to you.
You know, there is an enormous satisfaction in discovery. All of us on this panel,
it's a joy.
It is a joy, had their eurekas. Mine was as a young man battling with a theorem. And this theorem stayed with me when I was jogging, when I was eating, when I was showering. It was an obsession with me. And one night, all of a sudden, I saw the pathway. And I didn't believe it, and I just quickly got up and got a pad and pencil, and I jotted down just a very quick sketch. And I said, I'm sure this is wrong. And I went to sleep, and I got up in the morning, and I looked at it, and I thought about it, and I had the breakthrough. And I must tell you, in the most sincere terms, that to me was one of the highlights of my life, being able to see something that somebody else had not seen, which I had personally valued. And I think all scientists, serious scientists, have that moment. And if they're truly blessed and they're lucky, they have a number of those moments. And the joy cannot be transferred until you really experience it yourself. I think we have time for one more question. Yes?
My name is ARIELA. I'm an art major in Brooklyn College. My question is for Professor Filbin. Based on the research you're doing now, do you think that you're going to be able to help paraplegics in your lifetime, or how advanced do you think your research is going to become in the next few years?
Well, as I said, I'm cautiously optimistic. Now, I think the treatments that are coming along are going to help people in wheelchairs. Now, they may not be able to get up and walk again, but it may, for a quadriplegic, maybe be able to lift an arm, which gives it a lot more independence. For a paraplegic, maybe it's bladder function. And these are the things that we don't really think about. I never thought about them until I started working on the problem, that it's not necessarily the ability to walk that is the primary objective of someone in a wheelchair, but to get back a little bit of independence and dignity. And they're also in a lot of pain as well. So those things, maybe we don't need to get big, long regeneration of nerves. Little short regeneration may restore bladder function, may restore the ability to lift an arm or to hold a cup or something like that. So I would predict that in 10 years there will be routine treatments for spinal cord injury.
Thank you, Professors Akins, Filbin, Sarachik, and Lou. And thank you, ladies and gentlemen of our panel in the audience. Students, you're our hope. You're what we all work for. And the degree to which this exchange tonight helped you in your own directions is something that I hope we all accomplished. Thank you, ladies and gentlemen, for joining us at this special event of CUNY Honors, and we look forward to seeing you at our next opportunity.